Quantum numbers are used to describe where an electron is in an atom. In other words, the quantum numbers give an electron's address. There are 4 quantum numbers. The first one is called the principal quantum number, symbolized by n, and n takes the integer values of 1, 2, 3, and so on. N corresponds to the energy level of the electrons. All orbitals having the same n are called an electron shell. So for example, the second electron shell consists of the 2s orbital and the 2p orbitals in any atom. The second quantum number is called the angular momentum quantum number. It's symbolized by an L. And L ranges from integers of 0 up to n minus 1. In other words, if n equals 4, then the second quantum number could have a value between 0 and 4 minus 1, which is 3. This number defines the type of subshell. If L is equal to 0, then that's an s orbital. If L is equal to 1, that's a p orbital. If L is equal to 2, that's a d orbital. If L equals 3, that's an f orbital. And we know this already, that for a given shell, the energies of the orbitals go s orbitals have the least energy and f orbitals have the most. The third quantum number is called the magnetic quantum number, m sub l. And m sub l has the value of integers from negative L to L. You might remember that if the second quantum number, that is L, if L is equal to 0, that's talking about s orbitals. If L is equal to 1, those are p orbitals. If the magnetic quantum number ranges from negative L to L, that means for any p orbital, the magnetic quantum number ranges from negative 1 to positive 1, jumping by integers, so negative 1, 0, or positive 1. So when we're talking about the magnetic quantum number, we're essentially asking a question something like what's at the top right corner of the screen. Which of the 3p orbitals are we talking about? You might remember that p orbitals all come in groups of 3, and in terms of three-dimensional space, you can think of a p orbital, which is a dumbbell shape, as one p orbital going left and right, one p orbital being oriented up and down, and then the third p orbital being oriented, say, front to back. The magnetic quantum number tells us which of those 3 orbitals we're talking about: the left-right dumbbell, the up-down dumbbell, or the front-back dumbbell. Similarly, here at the bottom of the screen, you might remember that d orbitals come in groups of 5, and so this magnetic quantum number tells us which of the 5 d orbitals in any particular subshell are we talking about. Are we talking about the one that is shaped like a pacifier for twins, or are we talking about the orbital that is shaped like a cloverleaf that's laying on its side, or cloverleaf that's oriented vertically, like so? That's what we're dealing with the magnetic quantum number. The last quantum number is the electron spin quantum number, and it has only 2 values, positive or negative 1/2, which we refer to as spin up and spin down. Pauli's exclusion principle says that no 2 electrons in an atom may have the same set of 4 quantum numbers. That is, an orbital may hold only 2 electrons, and they must have opposite spins. Pauli's exclusion principle says that no 2 electrons in any atom can have the exact same address. Each electron has its own unique set of 4 quantum numbers. So let's try a few examples. What are the values of n and l for the following sublevels? Now you should recognize these notations from your earlier studies with writing electron configurations. And if you can write electron configurations, you can very easily find the values of n and l for any particular electron. n is given by this coefficient out front here. In the first case, n is 2. In the second case, n is 3. In the middle case, n is 4. Here, n is 5. And here, n is 4. Very simple. The L values, which is the second quantum number, we give a value of 0 if we're talking about s orbitals. We give a value of 1 if we're talking p orbitals. We give a value of 2 if we're talking d orbitals, and a value of 3 if we're talking f orbitals. The n and L values for any electron in any of these orbitals look like that. Notice that the n value, which is the first quantum number, corresponds exactly to the coefficient that's in front, and the second quantum number is 0 if we have s orbitals, as in the case on the left and the fourth case over here. The second quantum number is 2 for d orbitals, it's 1 for p orbitals, and it's 3 for f orbitals. So let's write the possible sets of the 4 quantum numbers for a 4p electron. The 4p orbitals, as all p orbitals of course, come in groups of 3. Clearly, the first 2 quantum numbers for all of the electrons, for any electrons that appear in these orbitals, the first quantum number is going to be 4 because we're in the 4th energy level. The second quantum number is going to be 1 because p orbitals have a second quantum number of 1. Then, the third quantum number, we need to label these orbitals somehow. And they go from negative L to positive L. I'm circling it in the lower left. L is 1. So the third quantum number goes from negative 1 to positive 1. So this electron, for example, will have a third quantum number of negative 1 and a fourth quantum number, since it's spin up, of positive 1/2. If an electron is there, it'll have a third quantum number of 0 and a fourth quantum number of 1/2. For that electron, the third quantum number will be 1 and the fourth will be 1/2. Now we're going to do the spin down electrons. This one that I've added here will have a third quantum number of negative 1 and a fourth quantum number, since it's spin down, of negative 1/2. This one will go something like this: 4, 1, 0, negative 1/2. And the last one, 4, because we're in the 4th energy level, 1, because we're talking p orbitals, positive 1, because we're talking this particular p orbital, and negative 1/2, because we have spin down. So let's write the 4 quantum numbers of each of the 6 3d electrons of an iron atom. D orbitals come in groups of 5. Iron ends with 3d6. So we need to put 6 electrons into these orbitals, and then we need to tell the address for each of those electrons. Now the first quantum number is going to be 3, because we're in 3 d orbitals. The second quantum number is going to be 2, because anytime you have d orbitals, the second quantum number is 2. So all of these addresses are going to start with 3, 2. The third quantum number then ranges from negative L to positive L. So I'm going to label those orbitals in that way. So then all we do is we put an electron in there. What would the last 2 quantum numbers be for this electron? Well, negative 2 and positive 1/2. When I put the next electron in, again, we need to conform to Hund's rule, which says that for equal energy orbitals, and these 5 all have equal energy, each orbital must have 1 electron before we start doubling up. So we can't put electron number 2 in this same orbital that we put the first electron in. So this one is going to be 3, 2, negative 1, because that's the name of this orbital, positive 1/2. And we're going to keep going. 3, 2, 0, 1/2. 3, 2, 1, 1/2. And that fifth electron is going to be 3, 2, 2, 1/2. We need a total of 6 electrons, so the question, of course, is where does the 6th electron go? And the answer is, it doesn't matter. all of those orbitals are of equal energy. So we really can't say what the third quantum number is. We don't know, does it go in this orbital or this one or this one or this one or this one. Really, all we can say about that sixth electron is that it's going to go 3, 2, something, negative 1/2. It's definitely going to be spin down. Just for fun, I'm going to put it in the middle orbital, but there's no energy preference one way or the other.